Okay, so today we're going to talk about two theories of dark matter production. So, dark matter is this invisible form of matter that's going to only interact through the gravitational force, meaning we can't detect it through traditional means, but it's going to contribute a lot to the makeup of the universe. It's going to hold things together, and it's going to actually make up a lot of the mass of the universe, so it's very important. But what we're looking at today is two theories of how did we get here with the amount of dark matter we have and the constant amount of dark matter. So how did it come from the early universe to this constant density of dark matter in the universe today? So let's start. We have two theories here called particle freeze-in and particle freeze-out. So we'll start with freeze-out. Freeze-out is the more recognized theory. It's the kind of leading dark matter production theory of the two. So freeze out, what's kind of going to happen with freeze out? Well, we're going to start with weakly interacting massive particles, WIMPs, which is a little offensive to the particles, so I do apologize with that. And we're going to move on to relics. So what does that mean? We're going to start with particles that are only going to interact with two of the four fundamental forces. Gravity, which I'm sure you're familiar with, and the weak force. If you're not familiar with the weak force, just know, like the name suggests, it's a very weak nuclear force that's going to happen at very small ranges. That's going to be important. And when we get to relics, relics are just going to be particles that are only going to be able to interact through their gravitational effects. So even though these particles, these weakly interacting massive particles, are going to still be able to interact with the weak force, the conditions for that are not going to be met, so they're only going to be seen interacting through gravitational effects, which we'll get into more of when we start explaining this. And why do they need to be massive? Well, because the dark matter we have today is cold dark matter. If they were not massive, then they would be moving at speeds the speed of light, or close to the speed of light if they just had very small masses, which means they'd be hot dark matter, they'd be radiation, which is not going to be consistent with the current structure of the universe. So, what we're going to start with, if we're going to start with in thermal equilibrium. So what that means is whatever processes are going to produce these weakly interacting massive particles are going to happen at the same rate as the ones that destroy them. So these interactions that produce them we're going to call production, and the interactions that destroy them we're going to be a little flamboyant and call that annihilation. So we're starting with the amount of these weakly interacting massive particles is not changing because they're being produced at the same rate that they're being annihilated. And one thing to note about the production is that these particles will keep being produced as long as the temperature allows it. So the energy that's being stored within the temperature has to be enough, so this is that energy, that it's greater than the rest energy of this dark matter mass. If it doesn't meet this condition, it no longer has enough energy to produce these weakly interacting massive particles. So what's going to happen as the universe expands, both of these production mechanisms, freeze-in and freeze-out, are very dependent on the expansion of the universe as a driving factor for the change that happens. As the universe expands, it's going to kind of cool off. And that means eventually it's going to get to a point where it's no longer in thermal equilibrium because it doesn't have the energy required to keep producing these particles. Now what's going to keep happening is annihilation, because annihilation doesn't require this energy to produce anything. So if we make a little graph here, on the x-axis we're going to put the mass divided by the temperature. Using temperature to kind of show how this progresses is going to be a lot more accurate than using time, although this is directly related to time. So as it cools off, this x-axis here is going to go and increase, which you can kind of think of as the universe progresses. And then on the y-axis, we're going to use something called the co-moving number density. So what that means is we're just talking about the density of dark matter, but we're going to account for the expansion of the universe. Because if we just use the regular density, then it's not going to give us a very accurate prediction, because how do we know that decreases in density are from the amount of these weakly interacting massive particles decreasing, and how do we know that it's not from just the universe expanding? So the co-moving number density is going to account for that for us. So thank you, co-moving number density. And as we're going to start in thermal equilibrium, it's just going to be a flat line. Eventually, we're going to get to a little point here where it no longer meets the conditions for production. So it's just going to annihilate now, so it's going to start decreasing, and nothing's going to stop it, so it's going to annihilate down to 0. Okay, something is wrong. We have now reached 0 density of dark matter. We needed a constant density of dark matter that's equal to the current present day density. So what happened? How do we get from this to what really should happen? Well, like I said, it's going to have to do with the expansion of the universe. As the universe continues to expand, we're going to get to a point where the annihilation rate is going to be less than the expansion rate of the universe, which means these particles they don't have enough energy to be produced, and they can't even find each other to annihilate fast enough. They're going to be searching for each other to annihilate, but the universe is going to be expanding quicker than they can do that. So at some point here, that's going to happen, and this is going to pull off and reach a constant non-zero density. And if you increase the annihilation rate, this is going to happen at later times, and you're going to get less of these relic particles at the end, because now they're relics because they can't find each other to annihilate. There's not enough energy for them to produce, so they can't interact with anything other than gravitational effects from their mass. So that is particle freeze out. Now let's look at particle freeze in. Particle freeze in is going to be an analogous process, but in a way it's going to be kind of reversed. So we're not going to start in thermal equilibrium. So we're actually going to start with nothing in terms of dark matter particles. And what we're going to get to is we're going to get to feebly interacting massive particles. So what's the distinction between feebly interacting and weakly interacting? Well, weakly interacting, they still interact through the weak force. Feebly interacting, other than gravity, the only thing they can be able to interact with is just enough to be coupled to these standard model particles, which are just the regular particles we know today. We're going to call these bath particles because they make up the thermal bath that's characterizing these galaxies and these structures and situations. So the feebly interacting means that they're coupled to these bath particles, meaning every time these bath particles interact, they could produce one of these particles, but they're not going to interact with anything other than gravity. So as soon as they're produced, they're going to act as relics. But how do we get to a constant non-zero amount of them? Well, we're going to start with these bath particles. So we're going to start with a temperature sufficiently high that it allows for interactions that are going to produce these feebly interacting massive particles through their coupling to take place. So since that requires energy, we want a high enough temperature that can happen. And then the same driving factor of the expansion of the universe that's going to cool everything down slowly get us to a point where they can't be produced from their coupling anymore. They no longer have enough energy to do that. And we want to be very precise if we're modeling these freeze-ins that the coupling constants are going to be just right, that we get the right amount of dark matter. So if we make the same graph, I'm not going to label the axes because you already know what they are. It's going to start, it's going to increase, and then as it cools off, we're just going to get a flat line. If you change the coupling so that way they couple more frequently, then you're going to get more. If you change the couple less frequently, then you're going to get less. So they're actually going to progress towards thermal equilibrium. So with freeze out, once you get to that point where the annihilation can't match the expansion of the universe, it's called freeze out because they've now frozen out of their processes. They've frozen out of annihilation, they've frozen out of production, they're just relics. With freeze in, it's called freeze in because we're starting with just these bath particles, and they're going to be producing these feebly interacting massive particles, and then they're going to freeze into the universe once they can no longer be produced. They've been produced up to a point, and then that process is no longer allowed because of the temperature. So those are kind of these two production mechanisms that are leading theories for how we've gotten to the amount of dark matter we have today. And they're both called freezing because they're relating to the cooling that happens as the universe expands. Hopefully that was helpful, and I hope you join us next time for more big concepts.